So today we are going to discuss about fiber optics. Now here in this lecture, I will show you different types of fibers or optical fibers and how an electrical signal, rather an optical signal, is being transmitted via this optical fiber. So let us start this discussion with initially what is an optical fiber. Recently, dielectric fibers these transparent dielectric fibers are very much useful, or they have been developed to carry efficiently optical signals from one point or from one place to another. Now remember the term, that is, it is a transparent dielectric medium. Number one. Number two, the transmission is more or less efficient in terms of loss. That is, in every time whenever we encounter a transmission of signal from one point to another, the first and foremost important factor which comes into our mind, that is the loss of that signal from the transmitter to the receiver end. And in this particular part, optical fiber is the mostly efficient one, as because the loss of an optical signal or an electrical signal from one point to another, whenever it is transmitted through this optical fiber, it is minimum. So that is an important parameter which we must reconsider. Now these optical fibers are hairline thin flexible structures, and they can guide optical signal from one place to another. It actually consists of an inner cylinder. You just consider this figure. There are two figures which I have drawn, but just consider the first one. Here you will find that an inner cylinder and there is an outer cylinder. Now this inner cylinder is known as the core of any fiber, core of the fiber. So this is the core part, and the outermost cylinder is known as the cladding. The outermost part is known as the cladding. Now here you must consider that because the diameter of these fibers is large compared to the small wavelength of optical signals, so here the inherent wave nature of light may be neglected, and we have to apply the known laws of geometrical optics, which we have earlier studied in our undergraduate or in our plus 2 courses. Those laws of geometrical optics are applicable here to study the optical fiber or to study the fiber optics. Now the importance of fiber optics arises from the fact that an optical fiber can carry a huge amount of information by using a light beam as a carrier wave. Moreover, because of low cost, high reliability and extremely low losses, these all the functional, or these all are the important parameters which actually make the optical fiber or the fiber optics so much important in our communication life. So whenever we have to consider to we have to carry a huge amount of information, we must consider these optical fiber. Now a question may arise that if the diameter of the fiber becomes of the order of wavelength, what will happen? As I have already told that since the diameter of these fibers is large compared to the small wavelength of optical signals, here we must use the laws of geometrical optics. But if the diameter of the fiber becomes considerable or becomes of the order of the wavelength of the electrical signal or optical signal what we are going to use, so then the wave nature of light cannot be neglected. Wave nature of light cannot be neglected, and in this case light travels as an electromagnetic wave along the fiber, which is actually similar to that of a microwave propagation along a waveguide. So, but you don't bother as because these type of fibers are of very rarely used. That is thin variety of these optical fibers. So, what we have actually going to study in this optical fiber class, these fibers and the diameter of these fibers is large compared to the small wavelength of optical signals, and so we are going to apply the laws of geometrical optics here to study the properties of optical fibers. Now let us consider once again that an optical fiber consists of two cylinders. Number one is the inner cylinder, which is, I have already told that it is known as the core of the fiber, and the other one is the outermost cylinder, and it is known as the cladding. It is known as the cladding. Now the core and the cladding, both of these two cylinders made up of glass or plastic. They may be made up of glass or plastics, and now the function of the cladding is actually to add mechanical strength to the core, as because this actually helps to make the fiber more strong, and besides this, the function of the cladding is also to reduce the scattering losses at the core interface. So cladding is actually have two uses, have two applications. Number one, they provide mechanical strength to the core of the fiber, and besides it reduce scattering losses at the core interface. Now in my later part of my lecture, I will tell you about different types of fibers, and these different types of fibers, or rather optical fibers, can be classified on the basis of refractive index profile of the core and the number of modes propagating in the fiber. Now besides these two cylinders, sometimes another jacket is found which is actually covered the entire fiber. So now whenever the optical transmission takes place, actually the wave passes through the optical pulse, or the signal passes through only the core of the fiber, not the cladding, and we actually want that in any cases these optical signals must not pass through the core cladding interface. It must be inside the core of the fiber, so that the losses can be reduced. And that is the another purpose of the cladding material, that it actually reduces the scattering losses of an optical signal inside the core. Now let's talk about the different types of fibers. Let's talk about the different types of fibers. And as I have told right now, that depending upon the refractive index profile, and as well as the number of modes of propagation within the fiber itself, we can divide optical fibers into three types. But now let us consider two types of optical fibers, because these two types are formed depending upon the refractive index variation, and these two are the two pictures shown here. One is the step index fiber and the other is the graded index fiber. So there are two types of optical fibers depending upon the refractive index variation of a fiber. We can divide into two. Number one is the step index fiber and the other one is the graded index fiber. Now if the core has a uniform refractive index, then it is called a step index fiber. So whenever the core has a uniform refractive index, then it is a step index fiber. And for a graded index fiber, the refractive index of the core varies. Now how this varies? This varies, actually the maximum refractive index will be along the axis of the core, and then it decreases gradually as we move on from the axis to the core cladding interface. So as we move towards the core cladding interface, the refractive index of the core varies, and it varies gradually. Then the fiber is known as a graded index fiber. So depending upon the variation of refractive index of the core, the optical fiber can be classified into two. Number one is the step index fiber, where the refractive index of the core remains uniform, and the other one is the graded index fiber, in which the refractive index of the core has got its maximum value at its axis, and as we move on from the axis of the core to the core cladding interface, the refractive index gradually decreases. So these are the two types of optical fibers depending upon the refractive index variation of the core. Okay? Now as I have told that depending upon the number of modes propagating along the fiber, optical fibers can be classified as multimode fiber and monomode fiber. Multimode fiber, so depending upon the number of modes of propagation inside or within a fiber, fibers can be again classified into two. Number one is the multimode fiber and the other one is the monomode fiber. So multimode fiber, it actually, as the word suggests, that multimode means the number of modes propagating within the fiber is many, is greater than one. So multimode, here I have shown two types of multimode fibers. Number one is the step index multimode fiber. As you can see that two rays can be propagated within this fiber. So now as the refractive index is uniform, it is actually step index, but again since the number of modes of propagation is more than one, it is a step index multimode fiber, right? And now here in the second part of the second picture, you can see that here it is shown a graded index, but again a multimode fiber, because number of optical rays moving through the fiber is more than one. So this is a step index multimode fiber. This one is a graded index multimode fiber. I have not shown here the monomode fiber. Now monomode fiber is actually a fiber in which only single mode of propagation is acceptable. So a fiber in which only a single mode of propagation is allowed, it is a monomode fiber. And you can see that for a monomode fiber, it will look like this. So this is a monomode fiber. This is a monomode fiber. I think you can see the difference. Here only a single mode of propagation is allowed. So this is a monomode fibers. This is a monomode fiber. Only one ray is allowed. Only one ray or single mode of propagation is allowed within a monomode fiber. So figure now let us consider again the topmost figure of this picture, in which I have shown a step index multimode fiber. Now here you can see that the step index fiber has a relatively large core, and depending on the launching angle of the incident light into the fiber, there can be large number of different zigzag paths or modes by which energy can travel down the core, and it is the step index multimode fiber. Now the rays here traveling along the fiber, along the core of the fiber, it actually takes different paths. So different rays take different paths to reach the end of the fiber, and as the different rays take different paths to move along the fiber, it actually, or the rays actually take different time to reach the other end of the fiber, and this is known as the intermodal dispersion. This is known as the intermodal dispersion, or this is an error. This is an error which is known as intermodal dispersion. Why this intermodal dispersion occurs? This occurs actually because whenever or depending upon the launching angle of the light rays in the core, then the light rays take different paths to move along the core of the fiber, and as the light rays take different paths to move along the fiber, different rays take different time to reach the end of the fiber, and this difference in time, as because different rays take different paths to reach the end of the fiber, so there is a time difference. There is a time difference between the rays reaching the receiving end or the end of the fiber, and this actually creates the intermodal dispersion. I am going to talk about more what is intermodal dispersion and what is the calculation, the mathematical derivation behind the intermodal dispersion. So just for now, next we move on to the graded index multimode fiber. Here you can see that the problem of these transit time difference in the step index multimode fiber, there is a difference in transit time, but in the graded index multimode fiber, the problem of difference in transit time can be greatly reduced. Why or how it can be reduced? Actually, here the rays do not follow the zigzag paths. As you can see that these rays do not follow the zigzag path as they followed in the step index multimode fiber. Why these rays do not follow the zigzag path? Actually, here you may consider that what is a graded index fiber. I have already told about that in the graded index fiber, the refractive index of the core is maximum at the center of the axis, and then it reduces gradually towards the core cladding interface. So because the refractive index varies gradually or it decreases along the core cladding interface, the rays which enters into the graded index multimode fiber actually does not follow the zigzag path, but they actually move along but they refracted gradually, and as the refractive index is smaller near the cladding, so the velocity of light is greater near the cladding, so the rays spiraling around, they actually spiraling around near the axis take shorter paths and travel slowly, as because the refractive index is higher at the axis part, and hence velocity of light is smaller at the central region. So the rays spiraling around near the axis take shorter paths and travel slowly, whereas the rays spiraling around near the cladding take longer paths and travel at faster rate. Okay, so the rays which actually spiraling around the central of the axis or central of the core part, as because the core has the maximum refractive index, the velocity is minimum. So the velocity is minimum when the velocity is minimum for the rays which is spiraling along the along the axis of the core of the graded index fiber, and the rays which actually spiraling around the cladding or around the core cladding interface, it may take a longer path, but as the refractive index is smaller near the core cladding interface, the rays though take a longer path, but the velocity of the rays are actually higher there. So the transit time difference, is reduced or is minimum for the graded index multimode fiber. Okay, now let's come to the third part of the figure, that is in which I show a monomode optical fiber. Its core is made so narrow, that only one mode of propagation is possible or is allowed. The rays travel only parallel to the axis, and as because only a single mode of propagation is allowed or possible, so here no terms of intermodal dispersion is possible, or the problem of intermodal dispersion is practically eliminated for a monomode fiber. Okay, now among these three, the multimode step index fiber is the oldest. Among these three types, the multimode step index fiber is the oldest. It is actually least expensive, but it has the serious drawback of intermodal dispersion. So for long distance communication, this step index multimode fiber is not advisable. So for a long distance communication, this fiber is not used. Which fiber is not used? The step index multimode fiber is not used for the serious intermodal dispersion phenomena occurs here. So for long distance communication, a single step index multimode fiber is not used. Now because I have already explained that the transit time difference or the intermodal dispersion is reduced in the graded index multimode fiber. So the graded index multimode fiber has medium priced. Intermodal dispersion is not so much serious problem here, and it is widely used in medium distance communication. It is widely used in medium distance communication as because the intermodal dispersion is not a great problem here. But the monomode fiber, what about the monomode fiber? As in a monomode fiber, only a single mode of propagation is allowed. So a monomode fiber is relatively expensive. It is relatively expensive and requires laser sources. But here there is no intermodal dispersion problem. So this type of fiber is mostly suitable for long distance communication. For long distance communication, monomode fiber is mostly suitable. Okay? Any doubts? Any doubts up to this? Okay. Now, as I am talked about a little bit of communication here, I must consider another problem here in communication, or rather in optical communication, that is known as crosstalk. That is known as crosstalk. So this is a problem we encounter in optical communication system. So what is a crosstalk? Now let us consider that we have a number of uncladded fibers. Uncladded means where the cladding is absent. So we have some uncladded fibers and they are packed. They are packed to form a bundle. They are packed to form a bundle, and now light can leak through from one fiber to another, and this is known as crosstalk. So this is known as crosstalk, and recently this particular phenomena is eliminated somewhat, as because today only fibers having cladding are used. However, crosstalk is also there in today's optical communication, as because if a fiber is bent, if a fiber is bent sharply, now the angle of incidence at the core cladding interface may become less than the critical angle, and then, as you know, that to make sure that the light always remain inside the cladding, we must make this light ray, whenever it reaches the core cladding interface, the angle of incidence must be greater than the critical angle. And now if the launching angle, or if the angle of incidence is at the core cladding interface may become less than the critical angle, what happens? A part of light actually escapes through the core, and it actually makes the crosstalk phenomena again. So earlier, whenever uncladded fibers are used, there was a chance of crosstalk, and now if the angle of incidence, and now that part is actually eliminated, as because nowadays we always use a cladded optical fiber. But here also, while we are using the cladded optical fiber, there is also a chance of crosstalk, as because if the angle of incidence at the core cladding interface may become less than the critical angle, then a part of light can escape and may cause crosstalk. So crosstalk is an important error, is an important phenomena whenever we are going to discuss the optical communication system. Okay. Now we must know about some advantages of optical fibers over the coaxial cables, as because the main application of optical fibers is in communication, and the following and the advantages are that the channel capacity of optical fibers is very large. They can carry a huge amount of information within the fiber, within the channel. Losses are extremely low. and optical fibers are small in size and light in weight. So these are some of the advantages of optical fibers, or rather why optical fibers is nowadays so much important, so much famous in the optical communication or in the communication world, as because they are less expensive. The basic raw material, as because the basic raw material of fibers is silica, which we know that it is abundantly available in nature, whereas if you consider coaxial cable, then the basic raw material is copper, which is actually very much costly. And in future optical fibers are expected to be relatively cheaper. So after a few years or in future, in every aspect of communication, we must say that optical fibers are going to use randomly in every sector of communication. So this part actually I have talked about the different types of fibers. What is an optical fiber? Some different types of optical fiber. What are their uses? The advantage as well as the disadvantage of an optical fiber. Now let's go into some deeper, and now we are going to discuss about two parameters of an optical fiber, and these are the acceptance angle and the numerical aperture. Acceptance angle and the numerical aperture. So let's consider. So for this I have to remove this picture. So let's consider this is the axis and this one is the cladding part. This one is the cladding. So this is the cladding part of the fiber, and the rest of this is the core. Now if a ray enters here, let the point is A and the angle of incidence is θ1. Now this ray, following the laws of geometrical optics, now this angle let us consider is as θ2. Now the angle at which this ray is incident on the core clad interface, let this angle be θ3, and the point is here designated as part. Is it okay? So I have considered an this part is the core part. This one is the core part of the fiber, and a ray actually enters here. Then if this is the point C, So this is the path of the ray. This is the path of the ray, and outside the optical fiber, if the refractive index is N0. So here we consider a step index optical fiber. It is a step index optical fiber with its core and cladding having refractive indices N1 and N2 respectively. Right. Now here N0 is the refractive index of the outside medium. So N0 is the refractive index of the outside medium, N1 is the refractive index of the core part, and N2 is the refractive index of the cladding part. A light enters into the fiber. A light enters into the fiber which is incident on the entrance aperture of the fiber and making an angle theta1, with the axis. And here also you can see that theta2 is the angle of refraction. So by using Snell's law, we initially can write that N0 sine theta 1 is equals to N1 sine theta 2. So from Snell's law, we can write N0 sine theta 1 is equals to N1 sine theta 2. This is from Snell's law. Okay. Now let it be equation number 1. Now in order to keep the light inside the core, the angle of incidence, that is angle of incidence at the core cladding interface, that is theta 3 at the core cladding interface must not be less than the critical angle, that is theta c. So to keep or to make sure that the light inside the core, the angle of inside the core must remain inside the core part. So the angle of incidence theta 3 at the core cladding interface must not be less than the critical angle, that is theta c of the core cladding interface. And as you can see from this figure, that theta 2 plus theta 3 plus 90 degree is actually 180 degree. So theta 3 is nothing but it equals to 90 degree minus theta 2. So theta 3 is actually 90 degree minus of theta 2. Okay. Let it be equation number 2. Now as you can see that if the value of theta 1 or if the angle theta 1 increases, if the angle theta 1 increases, theta 2 also increases. If theta 1 increases, then actually theta 2 also increases, and it will make theta 3 decreased value. It will decreases the value of theta 3 as because theta 3 equals to 90 degree minus theta 2. So if theta 1 increases, which in turn increase the value of theta 2, and then it will result in the decreased value of theta 3. But remember, there is a critical angle, there is a value of the critical angle at the core cladding interface, and we must remember that value or the value of theta 3 must not be less than the value of the critical angle at the core cladding interface. So the angle so there is a maximum value. There is a maximum value of theta 1. There is a maximum value of theta 1 beyond which we can't increase the value of theta 1. So that particular maximum value of the angle theta 1, and this is actually known as theta A. Theta A, and that is the acceptance angle, theta A. So this is the maximum value of the so this is the maximum value of theta 1, for which theta 3 is not less than the critical angle, and the ray must undergo total internal reflection at the core cladding interface, right? So this angle theta A is known as the acceptance angle, and thus the acceptance angle is the maximum angle of incidence. So the acceptance angle is the maximum angle of incidence for which any ray is totally internally reflected at the interface and therefore transmitted without suffering any loss. Now, a cone of light of semi-angle theta A, if we draw a cone, by considering this value of theta A as the semi-vertical angle of the cone, then this particular cone is known as the acceptance cone. This is the acceptance cone. What does it implicate? It implicates that a cone of light of semi-angle theta A is known as the acceptance cone. So it actually means that any ray, if it enters through this acceptance cone, the ray will suffer minimum radiation loss, or this ray must go through the core interface or the core section of the optical fiber. Okay, and it will suffer total internal reflection at the core clad interface. So this is the implication of the acceptance cone, but this is not so much important here in this particular description or in this particular discussion. We want to determine the value of theta A. We must know the value of theta A as because this is the maximum value of the incident angle at the opening end of the fiber. So as we see that from equation 1, n0 sin theta 1 equals to n1 sin theta 2, and if we put the value of sin theta 2 as from equation 2, we have n0 sin theta 1 that equals to n1 sin theta 2, and as because theta 2 is 90 degree minus theta 3, so that will be make n1 sin 90 degree minus of theta 3, so it will n1 cos theta 3. Okay, now as I have discussed that for theta 1, that is the angle of incidence, for theta 1 equals to theta A, for theta 1 equals to theta A, for theta 1 equals to theta A, what will be the value of theta 3? Theta 3 is nothing but the value of the critical angle theta C. So as I have considered theta 1 equals to theta A, and theta A, as I have told, that it is the acceptance angle and it is the maximum value of the incident angle theta 1 for which the light ray must have total internal reflection. That means for this particular or this maximum value of the incident angle, the value of the theta 3 must not be less than the critical angle, or rather, if this is the maximum value of theta 1, then theta 3 must be equals to the value of the critical angle. So here I have considered this, that for theta 1 equals to the acceptance angle, the angle of incidence at the core cladding interface, that is the value of theta 3 must be equals to the value of the critical angle theta C of the core cladding interface. So let's put these values in this equation. So we have n0 sin theta A, n0 sin theta A. So this equation becomes n0 sin theta A is equals to n1 cos theta C. So this may be equation number 3. So we have n0 sin theta A equals to n1 cos theta C. Now, as we know again from Snell's law that sine theta c is equals to n2 by n1. We know that sine theta c can be written as n2 by n1. So here from equation 3 we have n0 sine theta a is equals to n1, and then cos theta c means root over of 1 minus n2 square by n1 square. That means root over of n1 square minus of n2 square. Now as n0 is the refractive index of the outside medium of the fiber, we may consider the value of n0 equals to 1. So we have sine theta a, therefore sine theta a is equals to square root of n1 square minus of n2 square. Let it be equation number 4. And this quantity, now if you want to put the value of n0, specific value of n0, then you may remain n0 sine theta a equals to root over of n1 square minus n2 square, and then this value, that is either n0 sine theta a or rather only the sine theta a, as I have substituted the value of n0 equals to 1 to reduce the equation, nothing else. So this quantity is defined as the numerical aperture. So n0 sine theta a or sine theta a is known as the numerical aperture of the fiber. Okay. So in this part we have studied acceptance angle as well as the numerical aperture, the value, and these two you can get it from this particular discussion that these two are actually the physical parameters of a fiber. It actually shows that what will be the incident angle or what will be the incident angle of the launching angle of any optical pulse, any ray within a fiber, so that it must not suffer any radiation losses or it must go through the fiber via total internal reflection. Is it okay? Any doubts? If you have any doubts, please mention. Or rather, I will move to discuss the intermodal dispersion. So now let's talk about, okay. Now Utpal, some technical glitches are there always in this type of classes, in this type of lectures, so I can't help it. This must be some technical difficulties, but beyond this, if you understand this part of the lecture, I will move on to discuss the intermodal dispersion. This is an important part. This is an important part of the lecture, as because I have already discussed that why this intermodal dispersion appears, why this occurs. So let's talk about the intermodal dispersion, and for this I have again considering this figure, and where a step index fiber is taken with the core and the cladding having uniform refractive indices N1 and N2, and here just only I have to consider the length of the fiber, as because it will play an important part. So let's talk about that the length of the fiber is L. Okay, now depending on the launch angle, there can be large number of different zigzag paths along which light energy can travel down the fiber. Now here I have already considered two different light rays. The first ray is along the core of along the axis of the core it moves. This is the first ray, and the second ray is ABC, the ray which follows the path ABC. So here I have also considered two rays, and let's find out the difference in transit time, what will make the intermodal dispersion a serious phenomena in any fiber or in any step index fiber. So if now the ray from the figure we can consider that the ray traveling along the axis, it will take the shortest time, right? So the light ray which moves along the axis of the fiber, it actually takes the minimum path and it will have the minimum time to reach the end of the fiber. And if capital L as the length of the fiber is taken as capital L, so the minimum time of travel, that is we may consider as T min, that is the minimum time of travel, it actually the length of the fiber or the distance, axial length, divided by the velocity of light in the fiber, and it will be C by N1, as because the refractive index of the core is N1. So this is the minimum time which can a ray may taken for moving from the receiving end to from the sending end to the receiving end, and it is the minimum time of travel. Now as the another ray is taken the path ABC, then here the ray refracted into the fiber makes an angle theta 2 with the axis, so the path length L. So if this is the length, this is the path length L, so the path length L traversed by the ray will be small l divided by capital L, small l divided by small l equals to capital L divided by cos theta 2. Small l equals to capital L by cos theta 2. Okay? As because for this triangle, if you approximate this triangle and if this is the capital L value, then capital L This is the base of this triangle. So capital L by small l equals to cos theta 2. That means small l equals to capital L by cos theta 2. Now the path length will be the longest when the ray is incident on the core cladding interface at the critical angle, that is theta 3 equals to theta c. Now because already I have considered that the value of theta 2 equals to 90 degree, the value of theta 2 is actually 90 degree minus of theta 3. So the maximum time, that is T max will be small l divided by c by n1, as because here the path length is small l, so it will be small l by c by n1. And now putting the value of small l, that is capital L by cos theta 2, so here n1 capital L by c cos theta 2, and now putting the value of theta 2 equals to 90 degree minus theta 3, or the value of theta 3 is nothing but theta 3 equals to the critical angle value, that is theta c. So substituting these values, that is n1 L by c cos then theta 2 means 90 degree minus theta 3, and I have substituted the value theta c for theta 3, and then we have n1 capital L by c sin theta c, right? Now we already know that the value of sin theta c equals to n2 by n1. So again, by putting the value of sin theta c, that is n2 by n1, what we have n1 square capital L by c n2, and that is the maximum transit time or the maximum time of travel for any ray which actually follows the maximum path, and the value is T max equals to L n1 square by c n2. Let it be equation number 2, and T mean must be our equation number 1. So now let's find out the maximum time interval between the rays at the output end, and it will be nothing but delta t, and which can be found very easily by subtracting T max and T min. So the maximum time interval delta t will be equals to T max minus of T min. Putting the value of T max, that is L by n2, L by c, let's take L by c common, then n1 square by n2, or rather n1L common, so it will be n1 by n2 minus of 1, n1 by n2 minus of 1, and let it be equation number 3. So you will find that this is the maximum time interval which may occur inside the fiber, and it is ln1 by c into n1 by n2 minus 1. Now as the ray travel with a speed of c by n1, now for this particular time interval, that is for this particular time, a ray must be spread in space by a length, that is capital L. Capital L equals to, this is the velocity of the light ray inside the fiber, and if we multiplied it with this interval, this time interval, that is c by n1 into delta t, so we have capital L into n1 by n2 minus of 1. Let it be equation number 4. Okay. So what is actually delta L? Delta L is the spread of a light ray, or if you consider this light ray as an optical pulse, then the pulse is actually spreaded. The pulse gets thicker and the value of the spread is actually this, that is capital L into N1 by N2 minus 1. So here, as we know, why I have derived this, I have shown you the spread of the pulse, as because I have already talked to you time and again that informations to be transmitted through the fiber are usually digitally coded and sent along the fiber as a series of pulses. So the difference of transit time has actually a harmful effect in the form of broadening the shape of the pulses. So the pulse actually gets broadening. It actually thicks, and then every time whenever this particular intermodal dispersion appears, then whenever the pulses spread, then every time there is a chance to overlapping of pulses, of successive pulses. So to make the transmitted signal readable, the time interval between two consecutive pulses must be large compared to the spread out width. So here we must consider that to make the transmitted signal readable, the time interval between two consecutive pulses must be large compared to the spread out width, that is delta L. So what we must consider that the intermodal dispersion, actually the intermodal dispersion limits the rate of signal transmission through the fiber. So the frequency what we are going to use whenever the optical fiber is used in digital communication, so the pulses, that is the frequency of pulses what we are going to propagate through the optical fiber, there is a restriction for the frequency of the signal used, as because whenever in a large communication, in a long distance communication, I have already told you that for long distance communication, this multimode step index fiber is never used. Because of these particular effect, that is the intermodal dispersion, as because every time when intermodal dispersion occurs, the pulses grades broadening. The pulses grade broadening, that means the consecutive pulses, if you can't deduce the value of this delta t, and if you go beyond the derivation of delta t and you make pulses, consecutive pulses so close to each other, then what happens that every time, due to this intermodal dispersion, these pulses actually overlaps each other, and at the receiving end, or the receiver may not read the information sent by the transmitter. So there is a restriction about the frequency of pulses used in this type of communication, and this arises due to the intermodal dispersion, right? Though I thought that another topic, that is the ray path in the graded index fiber, I must continue or go through this particular part of the lecture, that is the ray path in the graded index fiber. And but now, as it is over 1 hour of time, so I must say goodbye, and it will be continued in my next class. Okay, goodbye.